Okay, so we are going to be finishing up with sets and maps today, and we're going to have, again, about a half an hour lecture, and then going to turn you loose on the route intersection Topcoder problem. So we're going to actually do a couple things. We're going to look at a solution from 140, the moon glow. A couple students in the class came up with a really nice solution that I wanted to show you because it shows how you take advantage of constraints that are given on the problem. Then, quick look at operator overloading on the maps, and a quick look at big O notation, but very, very quick, just so you know what we're talking about, and then on to the route intersection problem. So also remember, a week from today, the midterm, you'll have actually the midterm in two phases. So on Wednesday in lab, you will have three codecessor problems, programming problems. You'll have all lab to do them. And then on Thursday, you'll have a paper-based exam. And just so you know, there will be a hexadecimal addition problem on that paper-based exam, and there will be a bit shifting problem, much like question 4, I believe, from the first midterm, because those were the two questions that many of you did poorly on, and those are very important concepts that you need to master. If you have questions about them, I went over the answers thoroughly in my exam video where I reviewed the exam. So if you have questions about how to do those bit shifting and exclusive OR operations or how to do hexadecimal arithmetic, go and look at the video for the exam. Okay, so and for Thursday, actually for Wednesday, you'll have a one-page cheat sheet front and back. I have not yet decided about Thursday, because Thursday you don't need syntax. Thursday you just need to be able to answer problems. So you may not get a cheat sheet Thursday, but Wednesday you'll have a one-page cheat sheet front and back. You will not be allowed to look at anything other than that cheat sheet in the lab. So it'll just be like in CS 102, codecessor, that's the only thing that can be on the screen. Okay, so questions? I think, okay. Other questions? Yes?
So did you just say adding hexadecimal?
Pardon?
Did you just say adding hexadecimal?
Adding hexadecimal. I'm not going to have you doing hexadecimal subtraction, but hexadecimal addition, you need to know how to do it. It's important for pointer arithmetic. Okay? Pointer addresses are going to be important as you move on in your computer science career, and you need to know how to do, because we show pointer addresses using hexadecimal, you have to know how to do hexadecimal arithmetic. Other questions? Okay, moving on then into, I just wanted to show you the solution to the moon glow problem for the first midterm. I've been meaning to show it to you, and there's been so many cancellations I never got to it. So if you remember, there was a series, you were given a file that has some scores, and then a name, and then more scores, and you're supposed to print out the maximum score for each person. So for Brad it's 80, Joe it's 30, Susie it's 80. And I placed some constraints. You know how Topcoder has constraints? I placed some constraints on the problem. So first of all, I guaranteed that the data was correct, that the file ends with a name. So I guaranteed that it ends with a name, and I also guaranteed that every person has at least one score. Okay, so this allowed you to actually come up with a very elegant solution to the problem. I must confess, I was so intent on just following the framework that I had laid out in class that I missed the elegant solution, but at least 2 of you got it, and kudos to those who did. And it's this solution right here. So what's going on? Well, I guaranteed that every person has at least 1 score. And I have to always initialize my max score variable for each person. So what better way to initialize it than to read the first score into max score? Because you're always guaranteed that a person has at least 1 score. So we certainly know that the file, we could start by reasoning, well, we certainly know the file begins with 1 score. So we can read that score into max score. Then we'll keep reading scores until we encounter a name. Now there may be no further scores, but that's okay. The loop will immediately exit in that case. But while we have scores, we simply check if the score we got is greater than max score, and if it is, we update max score. Now, I guaranteed that every set of scores end it with a name. It's an absolute guarantee. Okay? That guarantee is backed up by the fact that the file ends with a name. So when I'm done, there's no need, when I fall out of the loop, there's no need to check about EOF. It's impossible that there can be EOF given my guarantee that there's a name. So I can just go ahead and clear CN, read the name, and print out the maximum score and the name. Now I come back up to the top and there's one of 2 situations. Either there's another person, in which case it's an absolute guarantee that there's 1 score associated with it. Therefore, I can read that score into max score, thus reinitializing max score. Or the other alternative is there is no next person, in which case the CN statement fails because of EOF, and I just fall out and end the program. So this was a really elegant solution to the Moonglow problem based on the constraints that I provided in the problem. So I felt like sharing it with you because this is what we're trying to teach you, is how to think through problems, how to use constraints to come up with elegant solutions to problems. And this was a really elegant solution to the Moonglow problem based on the constraints I placed on the input data. Okay? So any questions about this solution? Okay. So moving on, we had one new concept today, and that new concept was with maps and the overloading of the I'll call it the array subscript or the brackets operator. So it turns out that you are allowed to do what's called operator overloading in C++. And what that means is that you're allowed to provide definitions for different operators. So in this case, it is the, again, square brackets operator. And you always have to pretty much look up what the so-called function signature is for an operator, because it's different from operator to operator. But roughly speaking, if you're looking to override one in the class, so in class map, in the STL, there is a overload for this operator. Actually, before I do this, I realize I'm getting ahead of myself, so I'm going to come back to this. I first want to show what's going to happen. Realize I'm getting too deep too fast. Okay, so we're still talking about this overloading, but this is what you can do with it. Let me first show you what you can do with it. So if I have, say, map string int, so let's say that this is a map of people and their ages. Okay, so we'll call it map people. And the way that we've been doing inserts is by saying something like people insert, say, make pair, say BVZ and 51. And that's rather clunky. So the good folks that have developed the STL library also have come up with a different way to do it, which is they overloaded the array subscript operator, and you can also put the key into the operator and do it like that, which is a much cleaner way of writing the insert. So it also automatically creates a pair consisting of the key BVZ and the value 51, and it inserts it into the map. So this is very nice. It's a lot easier to write than this, and I certainly encourage you to use it in your code. However, if you read the notes that Dr. Planck wrote, you remember that he wrote temptation, temptation. So this is kind of like the apple in the Garden of Eden, because it looks luscious and red and we really want to take a bite of it. Okay? Unfortunately, if we're not careful, it can also lead to our downfall. And the reason we have to be careful is that, first of all, if there's already a key by that name in there, it simply changes the value of it. It doesn't tell us, oh, there's an error, or it doesn't add a second entry. It overwrites it. So if an entry already exists, or if the key, if an entry already exists for that key, then the entry is overwritten. And in his notes, Dr. Planck gave a nice example. His example, he was computing the scores for golfers in the majors, I think in 2009. So Dr. Planck and I both love golf. And for all the golfers who completed all 4 Grand Slam events, he was computing their average score. Now the problem was that Tiger Woods and one other person had exactly the same score. And he was inserting based on the scores because he wanted to print out the scores in ascending order. So you kind of got a feel for who had the best average score. But the problem was 2 people had the same score. So when he tried to, he in effect had something like this, I forget, it was something like 287.5, and he inserted someone like, say, me, and then later he inadvertently tried, actually, he first inserted Tiger, and then he inserted another golfer, and the problem was it overwrote Tiger with my name. And that was bad because when he printed out the list of golfers, Tiger's name was missing. Well, you could have, if you were using a multi-map, first of all, you can solve that problem. And you also, if you tried to do insert, there might be an issue because I'd have to check. I forgot to check that before starting today. Alan, maybe you could do that quickly for me. See if insert would actually succeed on a duplicate, okay? But you need to be aware of this overwriting problem. The other problem that we have to be careful about is when we do retrieval, okay? That's an even bigger issue. So if we do retrieval, let's say we say score, or let's say, yeah, we say int age equals people nils. And let's say nils isn't in our map. We are not informed that nils is not in our map. In fact, what happens is it returns a default value. In this case, it returns 0. And you might say, well, I know that 0 isn't a legitimate age. Maybe. What if it's a baby? Then you would be totally wrong. Maybe that's my newborn baby that I just inserted with an age of 0. You don't know for a fact that 0 is an invalid value. So the other problem here is that if you retrieve a key that does not exist, you get a default value. And you may not be able to determine if it signifies that the key did not exist. So those are the two problems. So how could you overcome problem 2? What statement could you put in your program before executing age equals people nils that would guarantee that nils was in the table before I attempted it? So think of it as a guard statement.
Just try to find nils.
Very good, Gerald. Certainly, I could first try to find it. So I could say if people dot find nils not equal to people dot end. Okay, then I could do my assignment. So just be aware, if you're going to use this syntax, which I am all in favor of because it is a very clean syntax, just be aware of those two potential problems with it. Try not to get tripped up with them. Okay? Yes, Alan?
So insert does not insert if there's already one with that key, and it returns a pair that includes an iterator to the existing element and the bool and
Okay, we're good. I know what's being talked about. Okay? So, let's go back quickly to, not the New York Times, but to lecture notes. And if you go, remember, to the very bottom, last time we quickly talked about how the set returned on insert a pair where the first element was a pointer to the key. So if the insert succeeded, the iterator was appointed to the inserted key. If the insert failed because the key was already there, it was a pointer to the pre-existing key. And bool was a true-false indicating whether or not the insert succeeded. And the same thing is happening with map. The first one is a pointer to the entry, and a second is an indication of did the insert succeed. So the insert succeeds if the key is not already there, and it fails if the insert, it fails if the key is already there. Okay? So this is true for both a set and a map. This is not true for a multi-set or a multi-map, because with a multi-set and a multi-map, why should this insert succeed regardless of whether the key is already there or not in a multi-set or a multi-map? Because the keys aren't unique. So in a multi-set and a multi-map, the whole reason you use them is because you expect to have duplicate keys. Therefore, if you try to insert a duplicate key, that's a completely expected occurrence. And therefore, insert is supposed to succeed regardless. So you only get this indication of success or failure for a set or a map. Okay, so tying that back to what we're talking about here is that this operation will always give us an indication of whether the insert succeeded or failed, and in fact it will not allow us to overwrite an existing entry. If we try to do an insert, say, of now nils into there, if we try to insert another entry for BVZ, say 49, it will fail. But if I try to say people, let's just erase this. If I try to say people, BVZ equals 49, that's a complete success. And 49 replaces 51. Now this can be good. Sometimes that's exactly what you want to do, is to update the entry. So sometimes this is exactly the behavior you want. If it is, bravo. Okay? Perfect. But if it's not, then use insert. So we're good? Questions about that?
Is there a way for you to test the bool value?
Yes. So Gerald's question was, is there a way to test the bool value? And the answer is yes. If we go back to the example here and get rid of my ink, you'll see that here we are type defing, first of all, a string set, and then we are doing a bunch of get lines. So let's say we were reading names. Okay, let's say that's all it is. And we try to insert each name into the set, and we actually store the return value. If you look up here, that's our pair with the iterator and the bool. And since it's a pair, we can look at the second element, and that's the bool value. So if it's true, it was successful insertion. If it's false, okay. Now, anyone notice kind of something little nasty here about this syntax versus the syntax we've been using for a map or a syntax iterator to access the second field? Yeah. So for a map or a set, if we're using the iterator, we have to use an arrow. But if we are accessing the return value here, we are using a dot. Okay, so just got to be careful about this. The compiler will always catch you. Okay, so if there's an issue, the compiler will always catch it and give you an error message, and then you just change it. I have to admit, this trips me up all the time. I'm always forgetting whether to use a dot or an arrow. So if you find it hard to memorize, don't worry. The compiler will always let you know. Other questions about that? Okay. So, final thing for today, a very quick introduction to what we call big O notation. We will get into it much more later in the course. But big O notation, you will often see us say, well, this operation, this find operation, takes us order log n time. And you're thinking, ooh, what does that mean? Or I say, this insert operation in a vector, or I'm sorry, this insert, yeah, takes order n time. You're like, what does that mean? Okay, so we need to just quickly talk about what that means. So we've been talking about how important efficiency is. We want to try to get programs that run as quickly as possible, and you've seen me use the time command. So what we usually do to figure out the efficiency of an algorithm is we try to come up with a function t that represents its time that it takes to execute as a function of some n, where n is usually the size of the input. Not always, but typically n is the size of the input. And that makes sense, right? We would think that if the input is 1 billion names, our program should run a lot more slowly than if the input is 10 names. So we probably expect that the program's running time typically depends on the size of the input. So we try to come up with some function that expresses the running time of the algorithm. You often see things like maybe 3n squared plus 6n plus 8. Okay? So what we're saying is, abstract, you're thinking, well, what is this? Microseconds? Milliseconds? You can't really say. It's just a good way to think of it is the number of instructions executed. So roughly speaking, it's the number of instructions executed. So the running time is typically proportional to the number of instructions executed, right? And then you just have to figure out how long it takes to execute an instruction on whatever processor you're running your program. So this is kind of just a fancy way of expressing the number of instructions that are executed. Okay? And when we say big O, it's very simple. We want to abstract away all the insignificant terms and just focus on the biggest term. So what's the biggest term in here? As n goes to infinity, okay, as n gets very large, what term dominates all other terms?
N squared.
N squared. So we zero in on the n squared. And furthermore, we get rid of the constant because as n goes to infinity, well, what's the difference between infinity and 3 times infinity? Okay, so we get rid of the constant, and what we're left with is n squared. So essentially, big O, to get the big O, okay, so it's a two-step process, at least for now. To get big O, okay, 1, construct T of n. And of course, that's the hard thing to do. And that's the thing we're going to put off until later in the semester. Okay? Then we find the largest term. And finally, we strip or delete the constant. And that gives us the big O running time for our algorithm. Okay? So just to give you a quick taste, okay, we're always saying, oh, a vector takes order n time to insert, potentially in the worst case. And let's say we're inserting into location 0, so we have to move everything down 1 spot. So we say for I equals 0, I less than, say, v dot, actually we've already, let me do this again. So we're inserting into a vector. And we're doing it at location 0. Okay, so the first thing we'd have to do if it's called vec is we would resize it to be vec.size plus 1. Okay, so we resize it, we make it 1 bigger. Okay, then, see, we'll say for I equals 1, because we're going to start shifting things over by 1. And actually, we have to go from the end. We can't go from the front. So we won't say for I equals n. In fact, we will say for I equals vec.size minus 1, I greater than 0, I minus minus, vec of I equals vec of I minus 1. So we're shifting everything 1 space to the right, and then we can finally set vec of 0 to whatever it is we are, to our value. So that's the insert. Now, roughly speaking, if we were trying to count up the number of operations, and again, I'm just going to do it very roughly, there was one instruction here, kind of a costly instruction, but in essence, one instruction. Okay? There's one instruction here, and then this for loop, how many times does the for loop execute? If there's n elements in the vector, how many times does it execute? N times. So it executes n times, and there's one instruction here, and we always have to do the comparison, and we always have to do the decrement. So roughly 3 instructions are executed on each pass. So roughly speaking, we might say T of n equals 3 times n for the loop plus 2, because we have 1 here and 1 here. So we say it's order n because this is the biggest term. We delete the constant, and we come up with big O of n. And that's how we say it's order n. Now, when you're looking at it, this one, to say that it only takes 1 instruction is a little bit false. You'd have to know how the resize operates. But we're actually allocating a vector that's how large? How many elements? If the original vector had n, this one has n plus 1. Well, it doesn't seem like we could really, seems like allocating maybe 1 element of memory might be faster than allocating 1,000,000. We don't know. It depends on different things. So you'd have to look into the operation of that resize operation to figure out whether it's really a constant time operation or whether it's taking order n time. Okay, I believe it's taking potentially order n time because I think it may have to copy the contents of the existing vector to the new vector. If, and this is a big if, it has to find a new block of memory. Remember that vectors typically have a little extra space lying around because they know they may grow larger. So if this resize is able to use that little bit of extra space, we're good. But if there's no extra space, we'd have to find a completely new piece of memory. It's like moving the house. Okay? So that's a good analogy. So if we have another baby and we have an extra bedroom, that's no problem. But if we have a new baby and all the bedrooms are full, and we're not allowed to double up in the bedrooms, we have to move. Okay? Think of it that way. So the resize operation could potentially be order n. If we have no extra space, we have to move to a new position in memory, and we have to move all the contents. Yes, Alan?
While you've got that on the screen and while you're talking about sort of hidden runtimes of methods, thought it might be worth mentioning that vector has an insert method that looks neat and clean, but it does all that junk behind the scenes.
Yes. So Alan is making a good point. So a vector has an insert operation. I know this is getting. So you could say vec.insert, vec.begin, because that's a pointer to the first element, say value. And that looks very clean. And you're saying, that's just one instruction. I just got around Dr. van der Zanden's order n algorithm. No, you didn't. Okay? Because vec.insert, while it looks very clean, executes this algorithm. So Alan's point is you can't assume that every function you call takes order 1 time or constant time. You have to know what it does. And in this case, that insert really is taking order n time. Am I going to ask you a question about big O notation on the exam? No. But I am going to start using big O notation in class to compare the running times of different algorithms. And I just want you to realize when I do that, that what we're doing is talking about the biggest term in this running time equation. Okay? Because that's the term that ultimately dominates the running time as n goes to infinity. Ardlin. You thought the for loop would be what? The for, so you have to know how the for loop is executed or implemented. Okay? The for loop really looks like I equals, in that case, vec dot size minus 1 while I greater than 0 vec I equals vec I minus 1. And then at the end, I minus minus. So that's how the for loop is really implemented. You can't see it happening, but that's what the compiler is doing to it. In reality, the compiler essentially just takes a for loop, converts it to a while loop, which you can't see it doing. But if you look at this, you'd probably agree that each iteration of the loop essentially executes 3 instructions, right? So there's no extra instruction for, quote, the while. The while is kind of this check. No, it's not. Okay. So the keyword itself is not an instruction. The keyword in some sense is translated into an instruction, but yes. That's what I was saying. In effect, it is, but I don't want to get into it right now. Okay? So that's diving deeper than I really want to.
Right.
Okay?
Later on, that branch like dominates all the other things.
No, the branch is very fast. It's just a jump. The most expensive operation in here is the assignment.
I was thinking the branch can mess up the pipelining.
That's true. The branch can mess up the pipelining. So, okay. But, right. I mean, again, we're abstracting away a lot of stuff here. So we're going to stay with 3. You're right, and Arlen, you're kind of right in that the for loop, eventually there is a branch statement, but leave that to 160, okay, where they talk about assembly language programming. So those of you who had 160, right, you saw that loops were implemented with a branch instruction, correct? So you know that there is a branch instruction lurking. But roughly speaking, we say 3 times n. Other questions? We good? Okay. So I want you to now turn to the root intersection topcoder problem. So take a look at it and go to the problem description. If you don't have a laptop, whoa, why am I getting cat poochie again? Oh, I'm in colorful rabbits. Okay. There we go. Now we have little Dasdraperma. I wonder who comes up with these names. Does anyone know who, at least I kind of had an idea with cat poochie. Anyone have an idea with Dasdraperma? Nope. Okay. So Poochie is kind of a, here Poochie, Poochie, Poochie is a kind of endearing name for a pet. Okay, that's where I could understand at least cat Poochie. But usually Poochie would also be a dog. Okay, so take a look at that. Think about it for a couple minutes. Feel free to talk about it with a neighbor. See if you can figure out roughly how you might go about solving it. Don't try and program it up yet. Or if you think you have a good idea, start programming it up. Remember, it's okay to talk about it with a friend. Okay, let's chat about this for a little bit. Figure out how we could solve this, because this is always, before we start programming, you have to kind of come up with an approach to solving the problem. Okay? So it always, first of all, we need to look at the constraints. Okay? We look at the number of dimensions. Do we think the number of dimensions is fairly small or fairly big? Very big, okay? This is a universe we can't even begin to grasp. Okay? But what they are trying to do here is take away your option of using a vector to represent points. Okay? Because obviously she's only going to make 50 hops. That's the second constraint, right? Is that she only moves in each step through one dimension. And she's going to make at most 50 such steps, right? That's what this second constraint is all about. So she's not even going to come close to exploring all billion dimensions. Okay, so representing her travels using a vector is not really a great idea. Okay, so we might be thinking about, we may have to use other data structures. But before we can think about how we might use other data structures, we're going to have to think about how we're going to solve this thing. Okay, and fundamentally, we need to be able to, what's the fundamental thing we have to be able to figure out at each step? If she's been at that point sometime in the past. Okay? So it seems that what we need to do is come up with a good representation for a point. Right, where a point is an n-dimensional point. And if we can come up with a good representation for an n-dimensional point, then we can compare the new point with past points, and if there's a match, we know it's not valid, right? So then our question becomes, well, what's a good representation for an n-dimensional point? Doug?
A map of vectors.
Okay, so a map of vectors, and what would so Doug's suggestion is a map of vectors, and what would the vectors represent?
They would be like the dimensions.
The dimensions, so like maybe dimension 3 and I'm at location 8. Is that your idea? Okay. So
I guess just like the locations.
Right. So it's kind of like in dimension 1 I'm at position 3, dimension 3 I'm at 8, dimension 10 maybe I'm at 2. Okay. So that would work, although probably we wouldn't need vectors for this. Maybe an object or something, maybe a class where we had, say, dimension, and we might have ID and location. Might be a better, but a map, if you're going to say map of arrays, probably, if you're going to use an array, would probably be better because you know they're all 2 elements. Vectors are kind of clunky. Okay, so it's an idea, and it's certainly one that occurred to me too when I first started, but it's not going to be easily able to compare these. So it's definitely a representation, but an issue here is we can compare them, but we're going to have to iterate through. For each point, we're going to have one of these maps, right? So to compare them, we're going to have to iterate through 2 maps and make sure that all the entries are identical, correct? So that's a little cumbersome. It works, but what I want to work on is a better, a more easier representation to deal with. Yes?
I was thinking a map of maps in which the map is actually like the key of like an outer map.
Okay, so a map of maps.
Because I was thinking the inner map could be like, the inner map, its keys would be the individual like coordinates, like the
Okay, so the individual coordinates.
and the values would be like, since it starts at the origin, it's at 0.
Okay,
The
so
value would be 0, and then so we have like several of these kinds of maps as the keys.
okay,
to
give
get
me a concrete example. Can you give me a concrete example? Let's say we had this. Let's say that this was one of our points.
And we have then like in our map, then we have like one map where like one map where like one key is like the first coordinate and the second key is the second coordinate, and that's all like, the value corresponding to the first key is 1, the value corresponding to the second key is 3.
Okay, so the keys represent dimensions like 1, 3, and 10, or
Yeah.
not?
And the values represent like their value.
The places that you've been, or
Yeah.
okay, so it
like,
might.
like 1, 1, like a 1, 3, 1, 10.
Okay.
2, 8, 2, 2.
Okay, so I think you're going to be kind of getting a little bit toward this solution here. Okay, I may not be understanding it correctly.
It's a
I
map
could-
of like it's a huge map of unique positions on like an n-dimensional plane, with all the values being 1. And if any of them were repeated, then it's like like one of the unique positions. It's like it used to be
Okay.
1, now it's 2.
Okay,
So that
so
means it's not valid.
okay, so I have to admit, I guess I can't quite wrap my head around it. If I could, I would try to explain it back to you, but I can't. So I'm going to move on because I have another solution in mind that doesn't involve maps. It may work, okay, but I have a solution in mind that doesn't involve maps. So I'm going to push you in the direction of I'd really like to be able to represent my point as a string. Because if I could represent a point as a string, I could do a string comparison. A string comparison is a pretty simple operation to do. Okay? So if I could represent my points as strings, someone think of a representation of a point as a string. We'll start.
You have a string of int characters, and you can mint the character count in each string if you need to.
Okay, so what are the characters going to be?
The characters are the location in each dimension.
Okay, the location, so 3, 8, and 2 from this example up here.
So if it was like an x, y, z, then you have 3 as your x coordinate, 8 as your y.
Okay, so 3, 8, 2. So basically, the string is going to be, in this case, we assume there's a dimension 0. So 0, it would be 0, 3, then 2 is 0, then dimension, so let's see, this is 0, 1, 2, dimension 3 is 8, then a bunch of zeros. And then at 10 we have 2. Is that the idea? Because it certainly works. Okay? So this certainly works. The only issue is how big is this string got to be? 1 billion characters, and it's going to be really sparse, right? This is where I was talking about. We can't really represent this using a vector because there's too many zeros here. This is a good start, but somehow we need to get compression. We need to get these zeros wiped out.
Does
Yes.
it really need to be a million long? Because there's only 50 moves, so there's
There
only
is, right. So the question is, how can we...
Any unique number in the coordinates vector.
Right, so it'd be nice if we only had to represent the unique numbers, which are 3, 8, and 2, the non-zero numbers. How can we do that, though? Because if I just have a string that is 382, I've lost all the information about the dimensions they correspond to.
You just store pairs.
Yes, very good. So what if we store pairs? Okay, now I'm going to intentionally butcher the pairs. So I store 1, 3, maybe not intentionally butcher. So if I store 1, 3, 3, 8, 10, 2, this is my string. But really the string is 1, 3, 3, 8, 1, 0, 2. Well, we know that what we mean is this, 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 and this to the when it does the comparison, it may well think that it's just going to treat the string like this. It's going to lose, it's not really going to know. For example, it might think that this is dimension 13 and we're at location 38. So we have to have some way to delimit the pairs, right?
Just use any ASCII value that's not a digit.
Yep, so just anything that will delimit these things is going to work, okay? And what Dr. Planck did, and I'm going to use his, you could use a comma, for example. Anything works. He decided to use braces. So he did it this way, and I'm just going to do it his way because that's how he did it. But you wouldn't have to, any delimiter would work. So what he did was, for each pair, he put them in square brackets and put a comma. That just made it easy for him to print it out. Okay, it would be equally good if he had simply said 1, 3, 3, 8, 10, 2. That would have been equally good. It's a unique representation. He did it this way to make it easier for him to read and debug. Okay, so this is nice because this is a pretty compact representation for a point. Okay, and I will admit, when I first started thinking about it, I also thought about using maps. Map of vector occurred to me. Maps of maps occurred to me. And then I realized these weren't easy to compare, and so I switched over to thinking about strings, and I figured out I could use a delimiter like this. So normally, you shouldn't just go with the first idea that pops into your head. Okay? You want to see if you can't come up with something better. Sometimes you can't, and you just got to start coding. If you're up against a deadline, there's a limit to how long you can think about it. Yes?
What was the problem with the map of vectors?
So it's not, there's no problem with it other than it's going to be a little hard to compare. Because we want to be, when I write the code, I like to write code that's relatively easy to read and isn't too complicated. So this is fine. It's just that if I start trying to determine whether 2 points are the same, I'm going to have to iterate through both maps. And I'm going to have to check to see whether each pair of entries is the same. Okay, which is not going to be quite as easy, perhaps, as just comparing strings.
Could you not just have your vector, you have one map of vectors and have the same kind of paired off called sets like you do in your string? Because a string is a vector. So.
Right, but okay, this string here is actually just a compact representation of Doug's idea. Okay? It really is. All I've done is taken Doug's idea and flattened it into a string to make it somewhat easy to compare. So there really is nothing wrong with this map of vectors idea. In fact, I simply, in essence, said, can I come up with a somewhat easier way to represent that map that will make it easy to compare it? Okay? So, in fact, nothing at all wrong with map of vectors. Just, I was trying to come up with an easier way to compare it. And that leads us to the second thing, which is Doug actually hit on the way we should represent a point. This is a great way to represent a point. I mean I'm sorry, if as so this was, issue 1 was a good representation for an n-dimensional point. Issue 2 was how to efficiently update, what's her name? Little what? Little Daz. How to efficiently update Little Daz's position. Okay, because while having a string is not a bad way to represent points, it doesn't give us a particularly efficient way to update a position, because we would have to do a linear search through the string in order to find the right dimension to update. Is that clear? If this string is pretty compact, but let's say that Little Daz could move through 1,000 dimensions, that string would get pretty large, and it wouldn't be very efficient to do a linear search through the string. And it's not particularly good to keep a vector, because the vector would still have to be 1 billion elements. So Doug's approach works very well for efficiently updating Little Daz's position. We'll keep a map of the current positions. Okay, so the key will be the dimension, and the value, so this will be, the key will be the dimension, and the value will be the current location in that dimension. So this way we're only, even if there's 1 billion dimensions, if Little Daz has only been to 40 of them, we only have 40 entries in our map. Yes?
Are you assuming all the other dimensions are 0?
Yes. We're assuming that Little Daz starts at 0, 0, 0, 0, 0.
What if you go in one direction and go right back? Then you would have that dimension 0 in order to lead off of the...
So, very good question. So the question is, Little Daz, remember there's a string that tells us what Little Daz does in each dimension. So the string could be 1, 1, 2, 2, in which case what happens in coordinate 1, after the first plus, she's at 1, 1. And after the second thing, the minus, she's back to 1, 0. And the question is, do we delete this entry from the map?
Yeah, I think you will 1, 0.
I'm just saying this.
Yeah. So what I'm saying is, in dimension 1, she does a plus, which means she goes from 1, 0 to 1, 1.
But she starts at the origin.
She starts at the origin in every dimension. So let's say it was 3 dimensions, 0, 0, 0, 0. So 0, 1, 2. Okay, and the thing says in dimension 1 she goes plus. So now it's going to be 0, 1, 0. Okay? So that means we're going in dimension 1 from location 0 to 1, comma 1, right? And then when we say minus, she's stepping back, and we're going back to location 0. Ergo, the question, what should we do with that entry? And there's two things you can do with it. You can delete it from the map.
I'm just saying the strings wouldn't match, but it would still be a repeated address.
So but it's okay for you to have a repeated address in one dimension. It just can't be in all dimensions.
But if that's the only operation, it would appear as a different string, but it would be the same address.
So in the string, though, okay, so in the string, just a second. So in the string, it would look like, initially, the string would look like 1, 1, right? And in the second time, the string would look like 1, 0. And you're saying, just a sec, and you're saying that initially, the string started out empty, correct? Right. So the problem is, what you're saying is this string and this string are different, yet they should be the same. So the solution, there's two solutions. One is that when you get back to the origin in a dimension, you delete that entry from the map. Okay, if I delete the entry from the map, it won't show up in the string, correct? In which case, we would be back to an empty string. So one solution is if I end up with a 0, I simply delete the entry from the map. The other solution, which is the one Dr. Planck adopted, was to be lazy. And he said, I'm going to leave it in the map, but when I iterate through the map, if I see that the value is 0, I'm simply not going to put it in the string. Okay, which achieves the same result of having an empty string. And his rationale for doing it is, well, little Daz might come back to this dimension, and it's kind of inefficient to delete it and then reinsert it. So the lazy approach says, we think Lady Daz will be back, little Daz. I want to call her Lady Daz. That she'll be back. Okay, so we're just going to be lazy and not delete it. But when we go through and print the string, if we see that the location is 0, we're simply not going to print that entry. So there's two solutions, and either one is good. Okay, I'm not saying either one is better than the other. They're both equally good. But you're right. We can't be putting an entry in the string. Any entry, any dimension that's a 0 does not belong in that string. Okay, so you're absolutely right. Okay, so we actually have a solution to our problem now. Okay, because we have a way to efficiently update little Daz's position. We're going to have a map, and the map is going to be pairs with a dimension and a location. And then each time we're going to, that we update her position, we're going to flatten that map into a string. So I'm going to say flatten map into string. And then what are we going to do with that string? That's the third thing. What should we do with that string? What do we need to do? She's been at a series of points. So when we get the string, what should we do with our strings? How should we store our strings? So that we can efficiently determine if one of them matches the current location. She keeps losing letters. Okay, what data structure is going to allow us to efficiently determine if one of them matches little d's location?
Could you use a set?
A set, very good. Why a set? It's a great.
Because if you try and insert it into the set, if it's already there, it'll return that.
It'll tell us that, whoops, it's already there, so we would know it's not valid. And why a set rather than a map?
Because it's only a string.
Because it's only a string. There's no value associated with it. Now, set came to your mind because that's what we've been banging on, right? And it's part of this particular lecture. Actually, I will tell you this. This is what Dr. Planck used. There's a better data structure in this particular case. Okay? The reason is an insert and is going to take order log_n time. We have a data structure that would give us this in order 1 time. Hash table. See, in this case, there's no requirement that we keep the strings in sorted order, right? So since there's no requirement that we keep them in sorted order, a hash table would actually be more efficient. But we're dealing in sets right now, so the actual implementation that Dr. Planck chose was sets. Plus, you may have gotten the message from his notes that Dr. Planck isn't particularly fond of hash tables. But the fact remains a hash table would be more efficient here. I just want you to realize why, because we're not requiring that the strings be kept in sorted order. Whereas in 2, where we're flattening the string, we have to print the dimensions out in sorted order. So there, it was really important that we keep the pairs in sorted order, right? So there, it really was important that we use a map rather than a hash table. Okay.
What if instead of the whole string thing, you used a set of arrays and a multi-set of arrays?
I think that's going to work too.
Yeah, and then you can compare the sizes of the two.
But the sizes isn't going to be enough because you could be in 2 different dimensions. The dimensions don't.
But the array can just be the point. Because it would be a 50-character long array because you only ever have 50 relevant dimensions.
Maybe.
So like you can represent the 12th dimension. If that's the first dimension that gets moved in, you can just call that the first because why not?
Right. It's possible. Let me come up afterward. Actually, come up and explain it because I think your approach works, but I have to think about it a little longer. The string approach definitely works. So I'm not going to make you code it up, but what I wanted you to kind of get out of this was how you think through a problem, how you select the data structures for solving it, and then now, only after about 30 minutes of talking about it and thinking about it, now you would be ready to program it up. Okay? We're not going to make you program it up. But I will actually post code so you can look at what the code looks like.
I think Planck posted